गुड मॉर्निंग एवरीवन. वी आर स्टडिंग एनिमल न्यूट्रिशन और आज हम पढ़ेंगे साइलेज. ओके, yesterday we studied hay. ठीक है, this comes under the conservation and preservation of feedstuffs. Okay, so that they can be used during the lean season and can be preserved and conserved during the flush season. Okay, as we already know that India has a deficiency of green fodder up to the level of 11 to 32%, and in the case of concentrates the deficiency is up to 40%. So we need to conserve and preserve these feedstuffs so that they can be available during scarcity and other lean periods. Okay, so today we will be discussing about the silage making, then we will discuss about the scarcity feedstuffs, feeding of animals, livestock during scarcity situations, some floods or disasters, other kind of situations wherein there is scarcity. Then third, we will also discuss about the processing of feeds. Okay, so various methods by which feeds can be processed, and it is a part of the feed technology unit. Okay, so starting our discussion with the silage making. So you already know what is silage. It is basically the processed feedstuff. It is a preserved green fodder. It comes under the category of green fodder, and it is the preserved green fodder under which there is controlled anaerobic fermentation of green fodder. Okay, so basically there is controlled anaerobic fermentation of green fodder, and the carbohydrates have been fermented, and thereby the lactic acid or the acid pH has been reduced. Okay, the pH has been reduced and it reaches up to the acidic level, due to which there is conservation or preservation of forage. Okay, pH goes up below the 4 or 4.2, alright, and lower the pH, better is the conservation and better is the production of silage. Okay, so we will discuss about the definitions, then the crops which are better and at which stages crops need to be harvested to produce the silage, then types of silage and the methods of silage making. Then we will also discuss about the AIV method, which is a scientific method, and synthetic artificial method. Then we will also discuss briefly about the physicochemical changes that occur in quality and the flag index. This is important. Sometimes it is asked in MCQs, okay, that what is the flag index, or with which condition, with which feedstuff it is associated. So it is associated with the silage. Then next, advantages. Sometimes some nutrient losses are also occurring inside the silage. Basically what happens, whenever there is leaching because of rainfall, then more of the nutrients will get lost, because water soluble nutrients will be absorbed, it will dissolve in the water, then it will get leached alongside the rainfall. Then afterwards we will also discuss briefly about the haylage, wastelage, silage and soilage. So these are basically confused. Sometimes we get confused between these terms, and these are also already asked in the MCQs also. So you need to remember and understand what is the basic feature, what do they actually mean. Then silage. So it is a conserved succulent green fodder or roughage which is stored in an airtight container. The airtight container here is called as silos. Okay, silos are the places wherein the silage is made. Then as I mentioned, controlled anaerobic fermentation takes place and its moisture content is basically retained. Okay, moisture content is basically retained. Okay, and it remains like a green fodder. The nutrient characteristics are rather sometimes enhanced as well. The crude protein content is enhanced when we add the NPN compounds externally, and sometimes the weeds that are present inside the alongside, they will get their anti-nutritive factor gets neutralized. Then there is minimum deterioration and minimum losses of nutrients. Okay, when we discussed about hay yesterday, we discussed how the losses of nutrients up to the level of 90% in the case of carotene. Then 20 to 30% dry matter losses are there in the case of green fodder. Then 10 to 15% in the case of grasses. So all these are the losses that take place inside the hay after making hay. But in the case of silage, these losses are very minimal. So nutritive nutrient quality and the quantity of nutrients is higher in the silage as compared to that of hay. Then ensilage is the process. Okay, silage is the thing that is made, and ensiling or ensilage is the process of conserving the green fodder as silage. And silos are the places. These are the basic places, structures wherein these anaerobic fermentation occurs. Okay, designed for storage and preservation of high moisture feed as silage. So the best silages are moist, soft but not slimy and fragrant. Basically, the fermentation should be controlled and not extensive fermentation should not occur, otherwise the protein material will also get hydrolyzed and the proteolysis will occur. That is not a characteristic of a good silage. Then ideal dry matter should be 30 to 35% of dry matter. Okay, this is important. 30 to 35% of dry matter should be present. Then the silage pH has 3.5 to 4.8 as 4.2 as I mentioned. Okay, the good quality silage has a pH of 3.5 to 4.2, and the dominant organism should be lactobacillus, lactic acid bacteria. Then silage color changes to dark brown. Dark brown color is because of pheophyting. Then the black color is because of excessive heating and it should be avoided. Silo depth should be, in the case of pit silos, these are constructed underground and in the pits, and the depth should be 2.5 to 3 meters. Then for 400 kg green fodder, 1 cubic meter space is required. Aerobic phase, in the beginning there is aerobic phase also, and all of the oxygen is utilized, and the plant cells are basically living at that time and they will utilize the oxygen. So, and carbon dioxide formation occurs. So that is the aerobic phase. The initial 5 to 7 days is the aerobic phase. Then as compared to hay, silage retains more beta carotene and vitamin E. Both of these get degraded in the case of hay because of photosensitive, because they are very photosensitive and unstable in the presence of UV rays. But in the case of silage, these two are basically retained. So the nutrient quality, as I've mentioned, these are higher. Then why do we need to conserve fodder, and why do we need to make silage? Basically, so it conserves the green fodder during lean and rainy season. Okay, then during the flush season, excess of the fodder, green fodder, can be converted into silage so that there is no scarcity condition. Then it also retains high moisture and palatability. Then it kills the weed, seeds and thorns. So lantana, awns, etc. can be converted. Basically, it neutralizes all the weed material. Then it reduces the digestive disorders as compared to dry roughage. Basically, it is highly palatable and better. It has a better buffering quality as well. Higher and better beta carotene and vitamin E retention than hay. So these are the basic reasons why we need to make silage. Then crops which are suitable for silage making and which should be their accurate harvesting stage. Okay. So in the case of cultivated grasses, so basically we want the fermentation to take place. Okay, fermentation should occur inside the silage. So that is the basic mechanism by which the silage is made. So for that, we need to have water soluble carbohydrates. Carbohydrates should be present. So the feedstuffs which contain higher compounds, higher quantities of water soluble carbohydrates are the ones that are good for silage making. And these include the grasses, okay, not the legumes. Legumes do not have higher content of carbohydrates, as we've already discussed during the initial classes, how legumes contain higher amounts of calcium, crude protein, etc. and vitamins, minerals, etc. Very nutritious, but they do not have the higher quantities of carbohydrates that needs to be hydrolyzed, then needs to be converted, fermented. But that is higher in the case of grasses. So if we want to conserve the forage in the form of silage, we will prefer the grasses, and sometimes the legumes are also used, but for them also either we will add externally molasses so that the carbohydrate content is increased, or we will include the grasses alongside in the ratio of 3:1. Basically, the carbohydrate levels should be increased in the legume fodder. So how we will do that? Either we will add the molasses, which is a direct source of carbohydrate, in the ratio of 3:1, okay, or we will add the forages, green fodder, the grasses alongside the legumes, again in the ratio of 3:1, okay. So through both these methods we will enhance the carbohydrates so that they get fermented. Then cultivated grasses, maize, sorghum, bajra, these are very good grasses for the fermentation, so best for silage. Okay, these grasses these are basically maize silage is the best silage, and oat hay is best. Okay, and best for silage, rich in soluble sugars, carbohydrates, etc. Soluble sugars, very important, soluble sugar, soluble carbohydrate. Then natural grasses, berseem, lucerne. Not natural grasses, these are legumes basically. So here it should be written legumes. So legumes, lucerne, berseem, these should be added with alongside. Okay, these should be added alongside molasses. As I mentioned, these should be added alongside molasses with 3 to 3.5% addition. Then cereal fodders alongside legumes. Again, as I mentioned, 3:1 ratio. Mixed in silage improves the quality. Then unwilted legumes, dry fodder alongside dry fodder with the ratio of 4:1. Then stage of silage making. Stage of harvesting for silage. Cereals at milky or dough stage, 30 to 35% dry matter. Basically, in every fodder you need to have 30 to 35% of dry matter. Legumes, tender pod formation stage. Grasses, half to 3/4 bloom stage. Then harvested between flowering, avoids excessive heating. Then too early means very low dry matter, and too late means digestibility is very less. We discussed about this in yesterday's class as well. Okay, very early there will be very high moisture content, very less dry matter content. So the stage of harvesting is important, and it should be cut at 2 to 4 centimeter length for efficient packing. Basically, the aerobic pockets should not be there, so we need to go for higher cutting, chopping of the forage. Then crops which are suitable, and then the additives that are added. Okay, molasses at 3 to 3.5%, just now we discussed. It provides the fermentable sugars, especially in the legume forage. It also improves the lactic acid bacterial growth. Then urea, 0.5 to 1%. It improves the nitrogen content, basically provides NPN. Protein enrichment is there. So the silage that is made after addition of urea will have a higher protein content. Then salt at the rate of 0.5%, it improves the palatability, and there is osmotic preservation itself also. Then sodium meta bisulfite. So sodium meta bisulfite is also, it also acts like a sulfur. It provides the sulfur. Okay, sulfur for the protein. Then partial sterilization also. Then checks bacterial growth. Then formic acid, in the case of AIV method we will add formic acid as well. There is rapid acidification, pH is reduced, and it inhibits the clostridial growth. Then sometimes bacterial inoculants externally, lactic acid bacteria, these are also added because they will promote the homofermentative lactic acid bacteria. Okay, best crops are maize, sorghum, bajra, which are rich in soluble sugars. Okay, legumes, and this we have discussed that 3:1 or 4:1 needs to be added, and 3 to 3.5% at the time of ensiling. Then what are the different types of silage? So the different kinds of bacteria are there. Homofermentative bacteria, heterofermentative bacteria, both of them are basically lactic acid bacteria. And then the butyric or the clostridial bacteria, which causes proteolysis. Then homofermentative bacteria, in this one molecule of glucose is converted into 2 molecules of lactic acid and two molecules of ATP, whereas in the case of heterofermentative, one molecule of glucose will convert into 1 molecule of lactic acid and another into ethanol and carbon dioxide. Basically heterofermentative, not all of this is converting into lactic acid, whereas in the case of homofermentative, everything will get converted into lactic acid. Here in the case of heterofermentative, ethanol and carbon dioxide will be present. Then in the case of fructose as well, 2 molecules of lactic acid bacteria. But in the case of fructose in the heterofermentative process, mannitol, acetic acid, carbon dioxide and lactic acid are also formed alongside. So that is why the homofermentative is most efficient. 85% of the total bacteria should be in the homofermentative phase, and hetero one is the lesser efficient. Then pH drops rapidly because see, if much of the lactic acid bacteria, lactic acid is being formed, then it is causing rapid drop in the pH, and there is excellent preservation. Whereas in the case of heterofermentative, pH drop is not that fast. Okay, because mannitol and the alcoholic compounds are also being formed alongside, and the carbon dioxide is getting lost. So it should not so heterofermentative is not that efficient, and the homofermentative one is the ideal fermentation type. Okay, so this heterofermentative is the one that occurs afterwards in the later stages. Then butyric acid and clostridial fermentation, this is not desirable basically. So this is caused by Clostridium under poor conditions. Whenever there will be growth of Clostridium under poor conditions, because Clostridia is also anaerobic bacteria. Okay, and butyric acid is formed here, which has a sharp disagreeable odor, and it also lowers the pH at 4.0, but it is not desirable. 60% of the total acids are poor quality silage, and it also produces ammonia. As I said, it is basically proteolysis. It causes the proteolysis of bacteria, proteolysis of feedstuffs. Okay, it causes the proteolysis of feedstuffs. So after proteolysis, ammonia is also released. So it produces ammonia, carbon dioxide and volatile fatty acids. It occurs whenever there will be excess of moisture or there will be poor packaging. So this is not desirable. Then classification. So the very good silage will have acidic taste, odor, and it should be free from mold, and the pH should be 3.5 to 4.2, and the lactic acid content will be very high. Ammonia nitrogen should be less than 10% of total nitrogen. Then in the case of good silage, also has acidic taste, but butyric acid content should be very less than 0.2%. Okay, it should be less than 0.2%. pH should be 4.2 to 4.5, and lactic acid is moderate, and 10 to 15% of total nitrogen is from ammonia nitrogen. Then the fair silage has some quantities of butyric acid. Slight proteolysis occurs. pH is 4.5 to 4.8, and slight ammonia will be present, 15 to 20%. The poor silage will be the butyric acid content will be higher. Okay, more than 60% of total acids is from the butyric acid, not because of lactic acid, and the more than 20% of total nitrogen will be from ammonia nitrogen. So it causes poor quality or the poor quality silage. The next is the method of silage making. So there are different types of silos, and as I mentioned, the silos are the structures in which the fermentation, the anaerobic fermentation, the controlled anaerobic fermentation occurs. So pit silo, these are basically dug. Okay, these are underground. So they are constructed after digging 2.4 to 3 meters. Okay, deep inside the earth. Then most common in India, variable sizes are there. Then tower silos, airtight structures are built above ground. These lead to better preservation. Then trench silos in horizontal pits. Okay, then polyethylene bags are also used sometimes. Polythene bags, 45 to 60 centimeter bags. Then in small scale, these are basically portable, but they are used at small scale. Then bunker silos, large horizontal concrete structures are built. Then what are the basic requirements for a silo? Walls should be impermeable so that water should not enter or should not exit as well. Okay, cement or brick, so that during rainfall also water does not enter, and these should be located on elevated ground, not too shallow and sufficiently deep. And then size should be calculated based on number of animals and the feeding period, so that sufficient quantities of silage is made. And what is the basic process of silage making? So first, the crops need to be selected. Maize, sorghum, bajra preferred at 30 to 35% of dry matter. So they should be harvested at correct stage, that is the milk or dough stage or half bloom stage. Then they need to be chopped at 2 to 4 centimeter pieces, because it will improve the packaging, and then the surface area will also be higher. Then wilting, if dry matter is less than 25%, then dry matter needs to be raised at 30 to 35%, because high moisture crops will lead to poor quality silage. Then after that, additives are also added. Sometimes urea, as I mentioned, 0.5 to 1% urea will be added to improve the protein content of the resultant silage. Then salt 0.5%, even molasses 3 to 3.5%. Then molasses becomes important in the case of legume silage. Then this need to be packed tightly so that there are no air pockets. Then after that, it should be sealed properly with soil or sand, and polythene film should be there. Then after that, it is allowed to ferment for 4 to 6 weeks, so that the lactic acid bacteria, anaerobic lactic acid bacteria, are very active. Then AIV method is another. This is the artificial method of silage making. So this was popularized in 1917 in America when lucerne was successfully ensiled. So lucerne is basically legume fodder. Okay, and legume fodder do not make good quality silage. So this is named after AI Vertanen. He is the person who devised this, later developed the method. Here HCl, sulfuric acid, is added other acid in place of other acid additives. Okay, and then in place of other feedstuff, lucerne is added, and in the place of acids, sulfuric acid and the HCl, both of these are added. So it is basically artificial acidification method. Dilute mineral acids are added to green fodder before ensiling to rapidly lower the pH and preserve the crop without fermentation losses. Okay, as I mentioned, sulfuric acid and hydrochloric acid are added. And then there is rapid pH drop, which inhibits the clostridial growth, mold formation and proteolysis immediately. No waiting for lactic acid bacteria to lower pH naturally. So this is important because there is more protein is retained, there is lesser proteolysis, and it is suitable for legume fodder, which is highly protein, which contains a good quality protein, crude protein. So otherwise it would have been lost through proteolysis. Then because these are difficult to ensile during normal process, so for them this AIV method is utilized. Acid handling is hazardous because these are very corrosive and also corrosive to equipments as well. So modern modification is there. After, in place of HCl, formic acid, propionic acid and other biological inoculants can be added alongside molasses. Then next, the physicochemical changes that occur during and after silage making. So during, as I mentioned, during the aerobic phase, what happens during the first 5 to 7 days, there is aerobic phase. The carbon dioxide is liberated and the oxygen is utilized. Then during the second stage, that is the anaerobic fermentation stage. Okay, and then lastly the stabilization phase. So see, the aerobic phase, in the aerobic phase oxygen is present but it is constantly depleted. The plants are basically live, they are plant cells are living at this moment, and then they will utilize oxygen continuously. So after they will utilize oxygen continuously, it will get depleted. Then there is a lag phase, and at this time the pH is normal because fermentation has not begun. It will begin at after whenever there will be depletion of oxygen. So afterwards, when there is depletion of oxygen, liberation of carbon dioxide, and then the anaerobic fermentation, because the anaerobic condition gets started after depletion of oxygen. So now the anaerobic fermentation begins, and then the production of lactic acid also begins, which leads to reduced pH. So this is the fermentation stage. So after pH reaches the 4 level, at pH 4.0, the stable conditions will start forming. It will stabilize. So these are the basic 3 stages. In the initial phase, aerobic phase, then lag phase for small time, and then the fermentation, and then the stable phase. So what happens during the aerobic phase? The residual oxygen is consumed by plant cells and aerobic microbes. Temperature rises 27 to 38 degrees Celsius because there is aerobic respiration. Carbon dioxide is produced, which creates the anaerobic conditions. Soluble carbohydrates are broken down by digestion process, glucose and fructose. Yeasts and molds are very active. Chlorophyll is converted into brown pigments, the pheophytin. Polyphenol oxidases are active and color becomes yellowish or brownish. Then proceeding to the second stage, that is the anaerobic fermentation phase. Lactic acid bacteria start becoming active and the pH begins to fall because lactic acid is produced. So it is the main acid that is produced, and it is indicative of good fermentation. Butyric acid may form if Clostridia is predominant, but we do not want that. Then proteases become active. Protein is broken down into peptides and then into amino acids. So sometimes free amino acids are also converted into ammonia and amides, which leads to nitrogen degradation. Not desirable. Then Maillard reaction, whenever the protein and soluble carbohydrate will react and form the brown color. Then lastly, the stabilization phase. pH stabilizes at 3.5 to 4.2. In case of lactic acid bacteria, whenever the lactic acid will predominate the silage, and it will be higher whenever the butyric acid will predominate the silage. Then proteolysis ceases. Proteolysis stops when the pH gets below 4. Bacterial activity also slows when the silage becomes set and it reaches the stabilization phase. Color becomes dark brown or black whenever there will be overheating. It will become black in color and it should be basically avoided. Then the beta carotene is partially preserved at 4.4 to 4.5. Then most vitamins, vitamin C, beta carotene partially lost, not much, and vitamin E is basically retained. So as we have already discussed, this is the changes that occur. Then the pH is initial pH is basically around 6 to 6.5. Why it is so? Because it is neutral pH. Basic pH is normal, neutral pH in initial phases. Then good silage has a pH of 3.5 to 4.2 and the poor quality more than 4.8, more than 5 even. The dominant acid, initially there is no acid. In good silage, lactic acid will dominate. In the poor silage, butyric acid will be higher. Ammonia nitrogen should be less than 10% of total nitrogen in good quality silage and more than 20% in poor silage. Then the color is dark olive or brown, and then in the case of poor silage, it will be black or putrid odor will eliminate. So basically these are the changes that occur. Beta carotene will be partially retained and mostly lost in the poor silage. So initially these are the changes, the characteristic features that you will observe, and in the good quality silage these will be basically preserved. The green color will turn into dark olive brown color, low ammonia, and then less than 10% in the good silage. So, and sometimes protein degradation also occurs. So this is the characteristic feature of a poor quality silage. The crude protein gets converted into peptides, amides. Basically this is the proteolysis that is occurring. Peptides, amides, then into amino acids, then ammonia and amines, and sometimes the histamine, tryptamine, tyramine, putrescine, these are formed and these are toxic to the animals. So these are biogenic amines, these are toxic to the animals. These will cause the toxicity symptoms inside the animals if the animals are fed poor quality silage. Then proteolysis rate is highest at pH 6. Basically whenever there will be higher pH, that is seen in the case of poor quality silage. In the case of butyric acid fermentative silage and the clostridial growth, then the ammonia nitrogen is present higher up to the level of more than 20%. So it indicates that this is the poor quality silage because the pH has not been reduced below 4. Then the biogenic amines, histamine, tyramine, cadaverine, putrescine, these are because of the decarboxylation reactions. Then, so what are the basic characteristics of a good quality silage? The texture will be moist, soft and not slimy or fragrant. Then color should be olive green, dark brown, pH 3.5 to 4.2, smell should be slightly acidic, fruity aroma and pleasant. Then lactic acid should predominate, 60 to 80 grams per kg dry matter in grasses. Butyric acid should be absent or minimum, less than 0.2%. The ammonia nitrogen less than 10%. Protein should be well retained and there should be minimal proteolysis. Then dry matter recovery should be high, minimum effluent losses. Palatability should be good because the animals will relish it. Then next the Flagg index, that is the feeding value score. Basically it is associated with the silage quality. So it takes into account the butyric acid content that is there, the main product of the saccharolytic clostridial bacteria. No reference to ammonia proteolysis species. Higher score means better quality silage and more TDN is present. So basically higher percentage of lactic acid shows higher Flagg score, and better TDN, better silage quality. Butyric acid reduces the Flagg score and score more than 30 is for the excellent silage. So what are the basic advantages? Briefly we have discussed this in the initial slides. So it conserves the green fodder during lean or rainy seasons. It retains more nutrients than haymaking. It kills the weeds, seeds, lantana, thorns, etc. and renders them, basically it improves the palatability, higher palatability, soft texture unlike dry fodder. It kills the internal parasites, larvae in the fodder. Then it also can utilize the rain-wet crops unsuitable for hay, but it can be utilized for silage making. Then beta carotene vitamin E is better retained than in hay. It is labor saving once made, easy long-term storage is there. No field losses due to rain damage versus hay making. It can also enrich protein via urea supplementation. So nutrient losses in hay versus silage. The dry matter losses in hay that we have already discussed around 20 to 30%, 20 to 40%. In the case of silage making, minimum 5 to 15%. Then protein losses 15 to 30%. We have discussed yesterday how protein losses was up to 28%. So 15 to 30%, these are the ranges basically. In the case of silage making, 5 to 10%. Beta carotene losses 70 to 90% in the silage, 25 to 40%. Vitamin E 50 to 70% in hair, 10 to 30%. Carbohydrate losses were around 25%. Moderate losses in hay making, and in silage there is low because carbohydrates are not basically lost, they are fermented. Then mineral losses low in both the cases. Then field losses high in the case of rain damage, but not in the case of silage because these are sealed containers. Then effluent losses are none in the case of hay making because there is no water loss, no effluent loss, but sometimes in silage making effluent losses will be present. Then silo filler disease, basically it is a disease that occurs because of silage. Then it is because of nitric oxide and the nitrogen dioxide, the oxides of nitrogen which are produced from high nitrate forages during anaerobic fermentation. So NO is the colorless gas, NO2 brown, then N2O4 a yellow color, and brownish fumes are sometimes liberated which are harmful. So these can also form nitric acid and it damages the lung tissue inside the body. They will damage the lung tissue, and then pneumonia and pulmonary signs and the classical signs that are observed during respiratory failure. It also oxidizes hemoglobin and forms methemoglobin or sulfhemoglobin. Basically methemoglobin, and there will be impaired oxygen transfer and the respiratory distress in the human beings and the those closely associated with the silage. Then avoid entering silo within 2 days and ensure that there is ventilation, and do not aerate the silo early. So these through these methods the silo fillers disease can be prevented. Basically it is an occupational hazard that occurs inside the bodies of the people that are associated with the silage filling. Then next, also discussing about the, basically we want to know whether you should know about these terms, okay, haylage, wastelage, silage and soilage. So haylage is basically, it is in between the hay and silage, and the dry matter content, everything that is in between hay and silage. In the case of silage, we discussed how the dry matter is 30 to 35%. Then in the case of hay, yesterday we discussed how the moisture content is 20 to 14%. See, if the moisture having 40 to 45% of dry matter before ensiling in airtight silo pits, so it is basically a high dry matter silage, 40 to 45% dry matter silage. So it should be half dried silage between hay and silage, and then dry matter 40 to 45%, wilted more than normal silage. The straws are chopped to fine pieces 2 to 3 cm, mixed with urea, minerals and water to enhance the nutrient quality, stored in silo pits, fermentation under anaerobic condition for 2 months, then fed with 2 kg green fodder per animal per day. So these are basically, it lies in between the hay and silage. Then wastelage, whenever the silage is made from waste material, okay, nitrogenous waste material, then it will be called as wastelage. Silage made from anaerobically fermented organic waste, animal organic waste, poultry litter, swine excreta, bovine dung, etc. So silage from the animal waste, feed ingredients, poultry droppings, etc. So it is called as wastelage because animal waste also contains other feed ingredients. Basically animal waste will be higher amounts of nitrogen will be there. So low cost field alternatives are there, and this will also reduce the environmental pollution. Then next, what is silage and soilage? So silage is also a type of silage that is made from industrial waste, and soilage is not silage. Basically it is whenever the animals are fed with the green fodder in there without grazing, okay, directly fed green fodder to the housed animals. So silage made from grain byproducts or wet industrial waste material, that is silage, distillery, spent grain, press mud, citrus pulp, etc. Basically industrial wastes. Then industrial or food processing byproducts. Example includes distillery grains, citrus pulp, brewery waste, press mud, etc. So these are basically rich in fermentable carbohydrates. We want the water soluble carbohydrates, soluble carbohydrates. So these are basically industrial byproducts are rich in these carbohydrates. Then silage, okay, fresh cut green fodder fed directly to the stall or shed without grazing. So there is zero grazing, green chop, also known as green chop or zero grazing. Basically, there is no fermentation in the case of silage. It is not fermented. It is not a kind of silage. So this was all about today's class. Now let's discuss briefly about the feeding of livestock during scarcity. The silage is also a type of feed, green fodder, that is fed to the animals during scarcity periods. Apart from this, there are other methods also involved in this. So, okay, why do we need to feed animals during scarcity? Basically, scarcity conditions are very widely formed. These are widely observed across India, because we have the deficiency of green fodder, dry fodder, and even concentrates. And also we have only 2% of the land area globally, but we have the higher quantities, higher amounts, higher population of livestock as well as human species, human beings. So there is greater chances and greater occurrence of scarcity period. So we need to be prepared so that we will prevent the losses which occur alongside during the scarcity periods. So we have 2% of the world's geographical area, yet 15% of the livestock population that depends directly on those, that depends on the 2%, very less geographical area. Then there is 16% and even up to 18% of the human population, which also competes with the animals for the concentrates. There is 40% concentrates deficit, and the green fodder deficit is 11 to 32%. So India has the world's best dairy buffaloes, draught cattle, carpet wool sheep, and prolific goats. So they need to be fed good quality fodder. Large livestock numbers, both asset and a liability in the feed competition. So only 2% rice, wheat, sorghum, etc. So that is diverted. So very less of the grains are diverted for livestock species, because human beings utilize them. So very less is available to the animals in the form of concentrates. Even the dry fodder is deficit up to 23%. Area under fodder crops is also severely limited. Then land increasingly diverted to cereals, pulses, oilseeds, and not only this, for industrial purposes also. Then when does the scarcity occur? Basically, whenever there is some disaster. So drought condition, whenever there will be failure of monsoon, so green fodder withers and well ponds also dry up. So in the case of floods, whenever the crops get submerged, then even during floods the concentration, the toxicity symptoms will be higher. Nitrates, okay, cyanide toxicity, all these will also occur because of droughts and floods. Then the crop submerged, hay and stored feeds get also damaged, swept away. Then third, in the case of cyclones and storms, the crop and the fodder destruction occurs, and animals also get displaced and sometimes die even. Then in this case of lean season during summers, there is no fresh green fodder and the stored dry fodder also gets depleted. Then whenever there will be market failure, rise in feed prices, so concentrates will be unavailable for the small farmers. So they will not feed the livestock species the concentrates. So their milk production will also get affected. Then directly it will also increase it will also cause shortage of the milk supply as well. And then the feed prices will also increase, and the milk prices will also increase, and it will cause a vicious cycle. Then post-harvest period, whenever there will be crop residue are limited, whenever there will be no byproducts available for the animals. Then during disease outbreaks also, as was in the case of lumpy skin disease, there will be feed hoarding, transport restrictions, quarantine will be there. So supply disruptions and supply shocks. So these make our country vulnerable to scarcity conditions. Then at these times, unconventional feedstuffs can be provided. Basically, unconventional feedstuffs are the alternative feedstuffs which contain sometimes the anti-nutritive factors. So their inclusion levels are basically lower, and sometimes the processing needs to be done. So So unconventional or non-conventional feed, a relative term that differs from the country to country. So in some countries these will be unconventional, but in others they are the major sources. So non-conventional feed resources refer to all those feeds that have not been traditionally used for animal feeding, either by farmers or by feed manufacturers in commercial feeds. These include agricultural and industrial byproducts, wastes, which have no value as human foods and can be used in animal feeds at certain percentages depending on their palatability, nutritional value, toxic, anti-nutritional factors. Okay, so what is basic necessity? Why do we need them? Because there is limited availability of conventional food or feed ingredients in India. To bridge the gap between requirements and availability of concentrates and refuges, to minimize the competition of livestock with human beings for conventional food grains, then for economic reasons because these are cheaper than the conventional feeds. Then as per ICRP, okay, All India Coordinated Research Project on Utilization of Agricultural Byproducts. So as per ICR, we need to go for non-conventional or unconventional feed resources. So there are multiple research projects that are undergoing. Then CLEFMA also uses these resources to formulate the economic rations basically. So these are the basic advantages, and that is why we need to go for unconventional feed resources. So what are the characteristics? So these are the byproducts of food production systems, and they are not used as such. Sometimes they are recycled, salvaged basically. These are cyclic, so these are recycled. Then they are mainly organic and can be solid, slurry or the liquid form. These are economic, these have economic value. These are basically byproducts, but still they have higher economic value. Then their value is lower than the collection and transportation, fallen tree leaves, etc. Field crops generating valuable non-conventional feed include tapioca and sugarcane because they have fermentable carbohydrates. So in the case of ruminants, they have high value. The majority are bulky, of poor quality, high fruit fiber, lignin content will be present. So they are suitable for ruminants and not for monogastric species. Some even contain toxic factors, as I mentioned, anti-nutritional factors like the castor bean meal containing ricin, the neem seed cake containing azadi ricin. Then considerable potential as feed materials, value can be increased by processing techniques. So these anti-nutritional factors can be eliminated by processing, so their value, economic value will be higher when they are processed. So there are two methods by which we can utilize the animal feed resources. First is the AICRP project, All India Coordinated Research Project. So they identified new feed resources, agricultural waste, industrial byproducts, the forest byproducts, and then they are conducting lab experiments, animal experiments also. Then methods have been developed to improve the nutritional quality of existing lignocellulosic crop residues for increased utilization. See, sometimes we also go for urea ammoniation, then we also go for urea treatment of the wheat straw, etc. to improve the digestibility. Okay, from 46% to 60-70% the digestibility is improved. The content of the crude protein is negligible in the wheat straw, but it is improved after urea addition. Then alkali treatment, steam treatment, etc. Then the classification and basic examples. So these fall into category of food processing residues, then crop residues, forest product residues, and sometimes the animal waste. In the case of energy supplements, the concentrates, these can be classified as concentrates providing energy supplements and concentrates providing protein supplements. Then for as roughages, top feeds and tree resources or agro-industrial byproducts. So starting with the concentrates, the mango seed kernel, tamarind seeds, basically TDN value will be higher in the case of concentrates as energy supplements. Tapioca, cassava waste, sal seed meal, then spent tea waste, babool seeds, pods, then sugarcane molasses 3 to 3.5%, tapioca chips, etc. Then secondly, as protein supplements, vegetable protein supplements, the cakes and meals basically, ambadi cake, then castor bean meal, neem seed cake, etc. Then Niger seed cake, karanj cake, rubber seed cake, all these are basically protein supplements. Higher crude protein will be present. Then as refuges, top feeds, tree resources, basically these are the forest byproducts, tree leaves, banyan, peepal, mango, teak, bamboo, all the tree leaves that are present, the groundnut shells, paddy husk, forest byproducts. Then the agro-industrial byproducts, the food processing industry byproducts, sugar factory, sugarcane trash, tops bagasse, sugarcane bagasse, molasses, press mud, etc. Starch industry, maize, germ, maize. So all these are basically agro-industrial byproducts. Then what are the basic byproducts that we will obtain from rice? Broken rice, rice bran, rice husk, rice straw. Then wheat, wheat bran, wheat straw, maize, maize bran, maize stover, groundnut husk, groundnut meal, groundnut straw, groundnut cake, etc. Sesame, sesame cake. All these are cakes that can be derived from oil seeds, different oil seeds. Then again meals can be derived from different oil seeds. Then soybean meal, then cotton seed meal, sweet potato, cassava leaves, etc. All these can be made, and these are the extraction rates. Then next, the tree, from the tree leaves also, neem. So these are the botanical names. All these should be in italics. So neem seed meal, so at the rate of 45 to 50% these are extracted. Then coconut meal, oil palm sludge, then rubber seed meal, mahua meal, okay. Then mango seed kernels, karanj meal, all these can be extracted. So even animal slaughterhouse byproducts can be utilized. We discussed this in LPG classes as well. Byproduct, blood meal, meat and bone meal, tankage, etc. Poultry industry, feather meal, offal meal, etc. But these need to be first sterilized, made sterilized, okay, so that they do not cause any disease. Abattoir waste meal, blood meal, tankage, etc. and animal organic waste. Just now we discussed how silage can also be produced from the animal waste. So waste plates can be produced in high moisture agricultural byproducts. Then, but there are certain constraints, okay, challenges associated with the unconventional feed resources. First and foremost challenge is that there is very high quantities of anti-nutritional factors, so they need to be processed first. Okay, then limited chemical and nutritional knowledge. The present status of knowledge is very limited, so we do not know what are the basic anti-nutritional factors and the basic challenges associated with them, feeding of them. So most of them contain the toxic factors, anti-nutritional factors. So detoxification methods are not that cost effective and easy for field application. Then second, non-availability in large quantities. So production of non-conventional feed or unconventional feed resources scattered, and in some cases quantity produced is too low, especially for processing at industrial scale. Then there is seasonal variability, okay. Availability is restricted to season and even geographically limited. There is no sufficient storage facility during season of availability. Then lack of technical skills, managerial technical skills. Then processing difficulties, as already mentioned, difficulties in collection, handling, transportation and processing. Then next, what are the deleterious factors or the toxic factors, anti-nutritional factors that we will observe? This is important. So ambadi cake, then banana waste. In most of these you will find tannins. Tannins will be very high. Rest we have already discussed this in our anti-nutritional factor class, how castor seed meal contain ricin, cassava seed contain HCN. In most of this you will find tannins, okay. Then cocoa seeds you will find theobromine, coconut plinth lignin, coffee seed caffeine and tannins, cotton seed gossypol. Then cowpea trypsin inhibitors. Then guar meal, trypsin inhibitors and gum. Guar meal, gum will be present. Then cotton seed cake, silk cotton seed cake, cyclopenoid. Then karanjin. Mango seed kernel, again tannins. Then neem seed, nimbine, tannins. Mahua seed, maureen. Okay. Then palm oil, high ash will be present. Rubber seed, okay, HCN will be present. Sal seed meal, tannins will be present. Sugarcane, lignin. Sugarcane bagasse, it is bagasse, not molasses, okay. In molasses you will not find lignin. Lignin will be in sugarcane bagasse. Then tamarind, then water hyacinth, oxalic acid. Then, so what are the basic optimum levels? Because of these issues, anti-nutritional factors, the optimum levels will be lower, okay. 10 to 20% are the basic optimum levels that you will find in most of these cases, 10 to 20%. Then these are the basic rations formulated for the feeding during the scarcity conditions, okay. You can refer them. So groundnut straw, okay, made from groundnut straw, maize grain, groundnut cake, de-oiled rice bread, Then in the case of urea, ammoniated wheat, straw, wheat bran, molasses, mineral salts. Then banyan tree leaves, maize grain, etc. So these are the basic examples of rations that can be formulated and fed to the animals during scarcity conditions. Now let's discuss about the processing of feeds and forage. Okay, so we have already discussed why feed and forage need to be processed. Just now we discussed in some cases in unconventional feed resources you will find anti-nutritional factors which needs to be detoxified before feeding to the animals. So that is done by processing of the feedstuffs. So in this lecture we will discuss the definitions, reasons for processing, why we need to go for feed processing, then particle size reduction methods, hammer mill, then grain processing methods, what are the basic principles, advantages, disadvantages, then the improving the poor quality roughages. For improving poor quality roughages, different processing methods, then what are the basic their principles, advantages and the disadvantages. So beginning our class for the feed processing. So feed processing, it is basically any procedure which will change the physico-chemical properties of the feed stuff and improve the feed quality, feed nutrient quality, and then the availability of nutrients. So it is any procedure performed on the feed ingredients or complete feeds to alter their physical, chemical and nutritional properties to improve their utilization for the animals. It includes processing of concentrates, grain, roughages, complete feeds using physical, chemical and even biological methods. Then in case of cereal, eggs, meals are exempted from sales tax under, okay, this is not that important. Then forage definition, then complete feed and feed compounding. The forage, we have discussed this in our initial classes, complete feed compounding. Then feed processing goals. Why do we need to go for feed processing? To improve the digestibility, palatability, to improve the feed efficiency and feed intake, and to reduce the anti-nutritional factors, reduce mold, salmonella, toxins. So there are multiple types of processing methods: physical, grinding, pelleting, rolling; chemical method, alkali treatment, acid treatment, urea treatment; then biological methods, enzymatic treatment, fungal and ensiling process; then thermal processing, steam, pressure, roasting. Then why do we need to go for this processing? So to make more profit, to increase the profitability. Feed efficiency improves up to 20% by changing the grain processing methods. Then second, to alter particle size, to reduce particle size. So reduced particle size will have higher surface area for digestion. To reduce or alter particle size by pelleting, grinding, cubing to enhance intake. Then to change the moisture content, basically higher moisture crops are susceptible to fungal intoxication and even fungal spoilage. So we need to reduce the moisture content so that they are better stored. So reduce to 10% for safer storage, prevent mold and salmonella growth. Then to change the feed density, to improve or reduce the density, bulk density. Bulky feeds, pelleted, cubed, increase energy density, reduce storage space. To improve palatability, molasses, fats, flavors are added. Dusty feeds are lesser acceptable even in case of horses. Then for improving the nutrient digestibility, starch 70 to 80% diameter gets gelatinized, so there will be increased digestibility. Okay, even the surface area is also improved, so there will be increased digestibility. Then to improve the nutrient availability, so protein availability is improved by processing of soybean and pulses, and even the anti-nutritive factor that is there, the trypsin inhibitors that is there, anti-vitamin E, anti-vitamin A that is present in the raw soybean gets reduced, detoxified. Then to detoxify harmful substances, trypsin inhibitors, gossypol, cotton feed, it also removes salmonella. Then to improve the keeping quality, preservatives are sometimes added. Even the moisture content is reduced to improve the keeping quality or the shelf stability. Then to lessen the mold and toxin, harvesting, drying, storage practices, critical treatment with ammonia acid sometimes also reduce the mold or toxin hazards. Then first beginning our introduction for the particle size reduction procedures. Okay, why do we need to go for reducing the particle size? First and foremost thing, to improve the surface area for the digestion of digestion and action of enzymes. Then also to change the secondly, to change the particle size, we need to go for changing the density also. Density is also changed after changing the particle size. So how we will do that? By cutting, crushing, shearing or impact grinding. 4 methods. By cutting, we will use a chaff cutter in silage cutter. Chaff cutter, basically chopping off the green fodder. Then crushing using ball mill or jaw crusher. Then shearing. Shearing is basically in case of shearing, cutting and crushing are also occurring simultaneously. Both of them occur simultaneously. Then impact grinding, hammer mill, jet mill. So cutting is accomplished by cutting, crushing, shearing, impact grinding, chaff cutter. Crushing, comprehensive force applied to reduce the particle size using ball mills, percussion mills. Then shearing, it is a combination of cutting and crushing in silage cutter, rotary bar. Then impact grinding, it uses impact to reduce the particle size, hammer mills, jet mills, etc. So ratio of coarse, medium and fine particles should be 1:6:3 for optimum ground feed. Then fineness should be 1:7. It gives no direct indication of proportion of fine particles. So Rotab sieve shaker is used for the fineness. Then bulk density. Okay, density means mass per unit volume, as you must be knowing that. It is measured by cubic foot test box. Then hammer mills uses the impact grinding. Roller mills use crushing. Then the difference between hammer mill and roller mills. Okay, so there is impact grinding principle. Hammers strike the material. Peripheral speed is there. Then central feeding tangential to the rotor. Then screen clearance. Number of hammers should be 15 per 100 mm of the rotor. So starch content is increased. Easier to grind with higher roughages. Then feed rate is directly proportional to the applied motor power. Then in the case of roller mills, 2 rolls rotate in the opposite direction. So there is crimping and crushing. Crimping and crushing is there. Then it is used for grains in Western countries. Roller mills are these are used in commercial mills. Then speed differential is there. Basically shearing is done through cutting and crushing. Both of them are applied here. Then there sometimes corrugated or serrated rolls are there. So different mixers are present, vertical mixer and horizontal. So after crushing and shearing, we will go for mixing of the feed ingredients. So there are 2 types of mixers, vertical mixers and the horizontal mixers. As the name suggests, in a vertical mixer, it is based on the shape of the structure, okay, and the mixture. So in case of vertical mixture, the cost is inexpensive. It becomes higher in the case of horizontal mixer. Then it is used for farms and it is used for higher. Horizontal mixture is used for higher and the larger feed mills. There is dry mixing, but in the case of horizontal, there is liquid mixing as well. In vertical mixer, there will be poor liquid mixing, but better quality horizontal mixing will have liquid mixing. Liquid mixtures can also be prepared through this horizontal method. So in the case of vertical mixer, lesser floor space is required, but in the case of horizontal, you will require more floor space because these are basically used for commercial mills. Then time will be lower in the case of horizontal mixer because it is more efficient, and time will be higher in the case of vertical mixer. Then power required, again horizontal mixer will require higher power. Then mixing efficiency will be better, okay, 95% in the case of vertical mixer and 99% in the case of horizontal. Then molasses and fats are more effectively mixed in the case of horizontal mixer because these are basically liquid substances, so they will mix better in the horizontal mixtures. Then the different grain processing methods. So these can be either dry processing method or the wet processing method. In the case of dry processing method, there is no use of steam or water or moisture. In the case of wet processing method, we will employ the use of steam or moisture. So multiple ways by which we can go for dry processing method: grinding, dry rolling, popping and puffing, micronizing, extruding and roasting. You need to remember the names of these methods. In grinding, as just now we discussed, using impact grinding, hammer mills or roller mills will crush the feed grains. Then these are the simplest and cheapest methods, basis for mixing, pelleting and then extrusion. So these are the basic steps. In first stage we will go for grinding, and then later on mixing, pelleting and then extrusion is also another method. Then dry rolling, the coarse medium grain is rolled to 1:6:3 ratio. It is suited for cattle, less effective in milch animals. Then popping and puffing, remember the temperature here, 700 to 800 degree Fahrenheit, 370 to 425 degrees Celsius for 15 to 30 seconds. Popping and puffing. It ruptures the starch granules and improves the consumption, 3 to 10%. This will improve the consumption from 3 to 10%. Then next is the micronizing. In micronizing, infrared rays are used. 3 into 10 raised by 8 to 3 into 10 raised by 11 microwaves per second. This is important. It gelatinizes starch and produces uniform dense product. Then extruding, moisture is 16 to 17% and temperature is 100 degrees Celsius. It also gelatinizes starch. It is used for pet food, lab animals, etc. Then roasting, 300 degree Fahrenheit or 148.9 degree Celsius. So it is done using flame. It inactivates the enzymes and inhibitory factors. So there is 5% moisture. So after extruding, the moisture level will be 16 to 17%, and after roasting, since the temperature is very high, the moisture level will reduce to 5%. Then the wet processing methods. So these are basically grain processing methods. So it can be dry processing or the wet processing methods. So soaking of the grains, 12 to 24 hours, grains are soaked in water and then offered to swine. These can be filtered. So these will also remove the toxic factors. Toxic factors will get removed after soaking. Then steam rolling, subjected to steam, then rolled. As was the case in dry rolling, same is the steam rolling. So there will be 25 to 30% moisture present. Then steam processing and flaking, using steam 50 psi steam for 1.5 minutes and moisture then to below 200 degree Fahrenheit temperature. Roll to thin flakes. It also gelatinizes starch. In pressure cooking, add 250 psi pressure for 20 seconds. Moisture to atmospheric pressure. So there will be low density product. Exploding, similar to popping, but here we will use steam. So temperature will be similar to popping. Exploding, sudden pressure will be used for the popped grain kernels. Then reconstitution, again using moisture. Moisture is increased from 10% to 12 to 30%. So these will reactivate the enzyme. So this was the important dry processing and the wet processing methods. So what are the basic principles involved, and then the advantages and the disadvantages. So grinding we have already discussed. These are the simplest and the cheapest method. Prerequisite for mixing, pelleting and then extruding. So what are the advantages? As we have discussed, it improves the surface area, increases the surface area, so the digestive enzyme process can access the grains better. So there will be improved palatability, improved mixing efficiency. It helps in pelleting and extruding. Then some disadvantages are there. Dustiness of the feed will increase. Too fine grading will lead to lower palatability in cattle. Okay. Lower palatability in cattle. Then propionic acid is there to improve the propionate ratio, loss of essential nutrients sometimes, and higher energy cost. Then fine grind, very fine grinding makes it gritty to ruminants, so they will avoid it. Then medium grind is best for cattle. Basically medium grinding is best for cattle. Then second is the dry rolling. So what are the advantages? Because it is cheap, easy, good for cattle and improves digestibility. But there are issues because it produces coarse grain. So not good for poultry. No gelatinization occurs. Less effective in milch animals. Then second was popping and puffing. We discussed the temperature. Then it ruptures the starch granules, so becomes highly digestible. 5 to 10% increased consumption, so there will be good palatability. But disadvantage is that high energy cost is there because temperature is very high, not suitable for all kinds of feed. Produces low density bulky product. Then micronizing, we used the 3 into 10 raised by 8 to 3 into 10 raised by 11 microwaves. So there is uniform dense product formation. Starch gets gelatinized. Infrared rays are energy efficient. But the disadvantage is that expensive equipments are required for its formation. Then limited to grains only, not for roughages. Then extruding process, again there is increased gelatinization, can be used for pet food, lab animals, etc. Bulk density is increased, and it also destroys the microbes. But the issue is that high cost equipment, moisture control becomes critical. 16 to 17% moisture should be present. it becomes critical, and it is not for all kind of material. Then again roasting, moisture content becomes very low, 5%, so storage is also storage conditions, storage quality is also improved. Then inactivates enzymes, inhibitory factors, improves the palatability of soybean as well. But there is risk of overheating, Maillard type reaction will also occur. Next are the wet processing methods. Important wet processing methods, important for the roughages even. Then these are the wet processing methods for the grains, okay. So first and foremost, the general method. So improved feed palatability, improved density, and then whenever the density will be higher, the storage space required will be lower. So no ingredient segregation, so there will be complete mixing of the feed. So feed wastage will be reduced. Animal will not show preference to the common feed. Then growth rate will be higher, heat labile inhibitors destroyed, then labor cost will be lower as compared to dry processing method. Then soaking, the simplest method. Grains are soaked for 12 to 24 hours in water. It removes the soluble toxins, softens the grain kernels. So it will remove the toxic factors, improve palatability, softens the feed, but the issue is that microbial growth will be there, sometimes fungal growth will be there, spoilage will be there if prolonged. Then pressure cooking at 250 psi for 20 seconds. The grains are cooked under high pressure. Very normally these are very much followed. Rapid starch gelatinization is there. It also kills pathogens. But high pressure equipments are required for very large quantities. We need to go for very high better quality equipments. So it is only suitable for the smaller farms. Then steam rolling. Steam rolling applied before rolling, grain get moistened to from 25 to 30%. Improved palatability, starch is partially gelatinized, but it requires silo infrastructure, and there is risk of spoilage because the moisture content is higher. Then exploding, steam pressure is required, sudden decrease to atmospheric pressure. Then it is similar to popping, highly palatable, highly digestible. Wheat and barley is used as dry rolled rations, but also reduced bulk density is it also increases the density. Then storage issues will be there. Then steam processing and flaking. Steam at 50 psi pressure, as just now we discussed. High starch gelatinization occurs, improved digestibility. Then pressure cooker, roller mills are required. Then reconstitution, increasing the moisture content. Again there will be issue that the moisture content will also be susceptible to spoilage. Next are the roughage processing methods. Okay, first we discussed how the grains can be processed. Now the roughage processing methods. So can be physical, chemical or biological. In the case of physical, soaking, chopping, grinding, pelleting, watering, then steam under pressure, then irradiation. In case of chemical treatment, alkali treatment, ammonia treatment, acidic treatment. Okay, then salt treatment, gases and oxidizing agents. Then biological method, using enzymes, cellulases, rot fungi, white rot fungi, then mushrooms, then canal process and the Z-resil process. So straws are basically low density and high cellulose, hemicellulose. Even lignin is very high. These are low protein, 1 to 2% fruit protein, sometimes no fruit protein. Then low digestibility of organic matter. So they are poorly digestible. So these are the problems with the roughages or the wheat straws. So we need to improve their nutrient quality, nutrient content. So lignin also binds with cellulose, hemicellulose, impedes the rumen microbial attack, and there is insufficient rumen degradable nitrogen. So we need to increase the digestibility, palatability and the voluntary intake and correct the nutrient deficiencies in poor quality roughages. So these are the methods that are followed, physical, chemical and the biological method. Starting with the physical methods. Okay, so chopping and chaff cutting, it reduces the particle size to 1 to 2 centimeter pieces, reduces wastage, improve the feed intake. Can be hand operated, manually or power operated, automated chaff cutters. So 75 to 100 kg per hour using hand or manual method, or 250 kg per hour using power method. Then soaking of the roughages. So soaking wheat straw removes the soluble potassium oxalates. It improves the calcium retention because oxalates level will reduce, but it does not improve digestibility directly. Then grinding by reducing the particle size and improving the passage rate. Rumination time get reduced. So fine grinding reduces the rumen acetate and propionate ratio. Then steam pressure breaks the chemical bonds between lignin and cellulose. The lignocellulose or the lignohemicellulose bonds get broken down during steam pressure. Then dehydration, removal of moisture content using very high temperature 600 to 1500 degree Fahrenheit for 3 to 5 minutes. Dry matter protein retained in dehydrated pellets 17% crude protein. Then keratin loss occurs. Then irradiation, experimental methods, breakdown of cellulose bonds, but commercially not such viable because microwaves and the irradiations are required. Then the chemical method using Beckman method, which followed the alkali treatment, NaOH treatment. So 1.5% NaOH of straw weight. It improves the rumen degradability by 60%. It breaks down the hydrogen bonds between cellulose and lignins. So the alkali treated straws are palatable, highly palatable, and dry or wet. So it can be either dry method or wet method. So modified Beckman method uses less NaOH and then the less NaOH. So it will be lesser toxic. So calcium hydroxide, second another alkali treatment method using 4% combined with 4% NaOH, which is more effective, also improves the calcium concentration. Then ammonia treatment. Okay, ammonia is produced by urea hydrolysis. Urea after hydrolysis produces ammonia and carbon dioxide via the urease enzyme. So ammonia will break down the lignocellulose bonds. So 3 to 3.5% urea will give 5.3% ammonia. So crude protein content will increase by 5 to 8%. 40 grams per kg dry matter is the optimum level. Moisture level should be 350 ml per kg or 400 ml per. Ammonia has fungicidal effect also. Then anhydrous ammonia treatment. So straw is wrapped in polyethylene, then anhydrous ammonia, that is without water. 3% anhydrous ammonia is added and then sealed. So the 5% urea at 40%. Paddy straw is treated with 5% urea at 40% moisture. Then lastly, the biological method for treatment of roughages. So white rot fungi, then Z-Resil process using pleurotus, then Carnal process. So in the case of white rot fungi, whose name is Coriolus versicolor, two kind of fungi can be used, Coriolus versicolus or Fenroseed chrysosporium. So 45 to 75% of lignin gets degraded in lignocellulose straws. Metabolic block in lignin, the Fenroseed is most effective and Coriolus degrades up to more than 45%. Then pleurotus. Okay, solid substrate fermentation occurs using pleurotus species. So straw is pre-treated with 4% urea, 0.1% calcium superphosphate and 0.3% calcium oxide, and then it is inoculated with Coprinus fimicarius. Then in the case of Carnal process, again solid substrate fermentation is used. Pleurotus, straw again pre-treated with urea and moisture, then pleurotus is inoculated, improves the crude protein content. So summarizing today's class, this processing methods, grinding is basically dry or physical method. There is impact or crushing. It is cheapest and it is basically important for pelleting process. Hammer mills have impact principle and the roller mills have crushing principle. Then popping, again dry or thermal method, 700 to 800 degree Fahrenheit, 15 to 30 seconds. Increases the starch availability by 5 to 10%. It ruptures the starch granules. Then micronizing, dry or thermal process, infrared rays 3 into 10 raised to power 8 per seconds or 3 into 10 raised to power 11 per seconds. Then dense and uniform product is produced, then infrared energy is used. Steam flaking, wet or thermal process, 50 psi pressure, steam alongside rolling. Gelatinization of starch, then reconstitution, wet method, 10% moisture is increased to 25 to 30%. So there is improved palatability and milk. 40 to 21 days can be utilized in silos. Then Beckman method, alkali treatment, chemical method. It breaks the hydrogen bonds in lignin and there is more than 60% rumen degradability. Then ammonia, urea treatment, ammonia is released from urease by the urease and urea. So crude protein content is increased. White rot fungi, just now we discussed lignin degradation, 45 to 75% lignin degradation. So these are the biological methods. Okay. So this was all for today's class. Last class Tomorrow we'll take the last class. In that we will discuss the quality, okay, quality of feedstuffs, and then in some species the requirements or the fundamental types of feeding strategies by thumb rule method. Okay, so that will be our last class tomorrow. So let's meet tomorrow for last class discussion.